So how can we go better and faster than 11N? And you probably heard about 802.11ac. So what do we do here? If you think about where we are, 11N allows us to do up to 4 streams and up to 40 megahertz channels. And the 802.11 people sat down and thought, so how can we do better than that? Well, if you think about it, you have 40 megahertz, 4 streams, we just doubled. Well, the first idea was to say, well, why don't we double again? So from 40 megahertz, why don't we use 80 megahertz channels or even 160 megahertz channels? That's the first idea. And same with the special streams. We say, you have 4. Why don't we do, I don't know, 5, 6, 7, 8? Why don't we do more special streams? And that's pretty much what 11AC ID was about. Of course, there's more than that, a lot more than that. One of them, of these ideas, to say also, why don't we improve the modulations? Now we have very good chips. We can do better than 64 QAM. We could do up to 256 QAM. So that's going to improve also the efficiency of the cell because you speak faster. And there are also some other mechanisms to also improve the conditions of the cell, not just improve the speed, but also improve the efficiency of the cell. So that's what drives the idea behind 802.11ac. One revolutionary item in those ideas is what we call MU-MIMO, where you say, why would we have only one single device sending at a time? Let's look at how that works. First of all, wider channels. We say, okay, you can double your channel size from 20 to 40. Now let's do more, 80 megahertz or 160 megahertz. That's the first idea. It's great. However, we say, well, probably 160 megahertz will be the access point, and stations are likely to be up to 80 megahertz. It's unlikely that we'll see a lot of stations using 160 megahertz because that takes a lot of energy, and stations typically have batteries. So maybe the AP will have that much, and maybe the stations will have a bit less. Also, where do you find 160 megahertz? Well, we know you do not find it in 2.4, right? Because if you look at 2.4, there is no 160 megahertz. The band itself is about 83 megahertz wide. So you may have one 80 megahertz channel, but there is no 2. So that just doesn't work. Anyway, the 802.11ac people saw that issue right from the beginning, and as a matter of fact, 802.11ac does not talk at all about 2.4 gigahertz. It's exclusively working in 5 gigahertz. There is a new effort which is called 802.11ax that is going to come maybe in a few years. And this one is trying to bring some features of 802.11ac into the 2.4 gigahertz band. But that's the future. For now, 802.11ac is only in 5 gigahertz. But even in 5 gigahertz, there is not a lot of space that allows you to use 160 megahertz. If you look at the channel list, and if you look at the 20 megahertz channel list, well, there is plenty, right? Remember all those. If you try to aggregate those channels, already you have some problems because some of these channels are green, as you can see, you can use them. Some of them are gray, you cannot use them yet, although there is some effort, as we said before, to try to get those, but they are not there yet. And if you look at the yellow channels, they are affected in most countries by DFS, by radars, so you may use them, but you may have to move away from them very fast if there is a radar. So already when you try to move from 20 to 40, you find yourself with some limitations. There are a certain number of green channels, and you can see we have 8 clear green channels that you can use pretty much in many spaces. But there are also some others that you cannot use, because if there is one gray part, you cannot aggregate channels with something that is gray. So 140 and 144, for example, you cannot use them. Channel 96, you cannot use it either in 40 megahertz because it would be tied to channel 92 that you cannot use. And if you look at the yellow area, now you have 3 channels that you can use in 40 megahertz, but are kind of risky because you may have to drop away from those channels. So that creates some issues in dense environment. And things get even worse if you move to 80 megahertz, because now you have only 4 clear, non-overlapping green channels, and the others are either gray or either yellow. Now, what about 160? Well, you see, we have a problem. There is 1. So how do you have more than 1 access point on 160 megahertz? Well, of course, there are a few more you can use, but you know, this one is risky because it's affected partly by radar, so you may have to move away, and the others are anyway in gray area, so you cannot use them. And you understand this is why there is such an effort to try to get more of these gray channels allowed for Wi-Fi usage, and also some space in the higher part of Unit 3, so we can have more than 160 megahertz channels. So the effort is ongoing. It's going to take a while because there are some other devices using those frequencies, and of course the rules are going to take different time to get some possibilities depending on where you are in the world. So in the end, if we can get those channels, the dream is to be able to have all those blue channels on top. These are the negotiations that are ongoing. And if this happens, of course, this is going to simplify a lot your deployment. There are still some channels, of course, that will be affected by radars because radars are not going away. But if you add the blue channels to the green channels, now you have at least deployment possibilities in 160 megahertz in enterprise environments where you will have more than one access point in any given space. The effort is ongoing, to be continued. The other item that 802.11ac works on is more special streams. We have in theory up to 4 in 11n, and they say, well, why don't we go higher and go all the way up to 8? Realize that is 8 radio chains, 8 radios in your device sending and receiving at the same time on the same frequency. That's a lot, right? That's a lot not only in terms of battery, but also in terms of channel utilization. Realize that you have already a lot of channels, 3, and each of these radios is going to send and be received by all the others. And because you have 3 signals sending at the same time, these receiving radios have to distinguish 3 signals, one from the other. And it's already very complex, and we can do it. But imagine if you have 8, that is to say 8 circuits sending each a different signal and sending it to all the others. And on the receiving end, each of the receiving chain has to distinguish the signal it's targeted to receive from the 7 others. And you receive that. So how do you tell the light blue one from the others? So you see, in theory, it's nice to go to 8 streams. Practically speaking, it's an engineering challenge. And so far, even with 11n that allows all the way up to 4 streams, it took the industry 6 years to be able to go all the way up to 3 streams. So going up to 8, that may happen one day, but it's going to take a while. For now, the next challenge is to get 4 streams, and that is coming. But 4 is going to be our max limit for a couple of years before we can get higher than that. So let's make use of these 4 and think about how we use those streams. Again, we said phones don't have more than one radio chain because of battery consumption. If you think about it, and if you think about the quantity of phones you have in your network, that's a gigantic waste of time. Because most of the time, you have access points that can have maybe 2 or 3 or more streams, and then you have a client that comes in and says, oh, I can do only one of the streams. So you have your access point that sends 1 stream, and 2 radio chains that are being unused. If you use beamforming, and we'll come back on that, maybe you will be using 2 radios to be able to shoot 2 signals identical to the client to increase the quality of the signal on the client, but you're still wasting one of the radio chains. So with 11ac, they thought, why don't we try to make the system a bit more clever? And if we can tell one stream from the other, why don't we try to use all the streams, but with different clients? So you have your 3 streams on your access point, and you have a client that comes in and says, oh, I can do only 1 stream. But you also have another client in your cell that says, oh, I can do 2 streams. And the idea would be to say, all right, you're going to send 1 stream to a client and 2 streams to the other clients at the same time on the same frequency. And those devices are going to receive the stream that's for them and discard the stream that's for the other guy because the MAC address destination is different. So we are going to use all the streams we can by communicating at the same time to different clients at the same time. There's a lot of complexity there because you have to make sure that the stream you send to one client is not going to disrupt the other client. But if you can make it work, then you double the efficiency of your downstream. Be careful, it's only downstream. 11ac doesn't talk about multiple streams upstream. When these clients are going to reply, they are going to reply one at a time. It's only in the down direction that you can send multiple clients. But it's very common that the AP needs to send too many clients. All right, so keep in mind, this is coming, MU-MIMO is going to happen, but it's challenging. So there are some limitations in MU-MIMO. In other words, it's not a magical way of multiplying the speeds in your cell. It's going to improve the cell conditions somehow, but it's not a magic pill. The other thing about 802.11ac that makes a lot of noise is 256 QAM. So the idea here is to say, well, 64 QAM is good because we can get some decent speed there. But why don't we go even higher and have more targets in our grid? 256 instead of 64. And of course, in theory, it's better because if you have more points in your grid, then each point can be more bits than before. So in 64 QAM, you have 6 bits. Now you can have 8 if you use 256 QAM. So of course, that's a lot better. You go a lot faster when you communicate because you mean 8 bits each time instead of meaning 6 bits. The downside is that if you do the math, it works well in theory. But if you look at the grid, you say, well, these points are very close to one another. And the downside is you may be doubling the speed, but you need to be close enough that the signal quality is going to be high enough that you can distinguish one point from the neighbor. And that's not easy. As a matter of fact, when you look at the grid, if you look at the number of points and when you try to communicate with the speed, you realize that if you're not very, very close to the access point, it's not going to work. So the consequence of using 256 QAM is that because the points are so close, each of the modulations you allow when using 256 QAM is actually a bit smaller, a bit slower than the modulation you can use with 64 QAM. You still go faster, but also you have to be very close to the access point. And we joke sometimes saying, when you have to be so close to the access point that your antennas are going to touch, is that still technically wireless? So joke apart, 256 QAM is fast, but you have to be a few feet away from the access point. If you are more than 10 to 20 feet away from the access point, there are very few chances that you can still achieve that kind of rate. And typically the access point is on the ceiling, so it's not very close to you. So 256 QAM is great, but again, that's up to type of speed. It's not the average speed you will get on average client. So what kind of MCS, what kind of speed do you get with 11AC? Well, pretty much the same speed as 11N, until you expand to 80 MHz, until you expand to 160 MHz, or until you expand to 256 QAM. But all that you see in black here is the same for 11N and 11AC because you use the same modulations, you use the same channel sizes. It's just that 11AC expands 11N to larger channels and more modulations. However, keep in mind that when you use 802.11ac, your header is going to mention that you use something which is called VHT, very high throughput, and that's 802.11ac. So although the speeds are the same in N and AC, it doesn't mean that you use the same protocol. You're labeling your frame with very high throughput, VHT, and that's 11AC, and that's not 11N. So if you send an 802.11ac frame to an 802.11n access point, it's not going to understand it, even if you send it at one of the common speeds. You have to have an 11AC access point to understand 11AC frames. But of course, stations that are 11AC are also 802.11n, so they can choose the modulation that matches what the access point can do. So that's for one stream. If you go all the way up to 8 streams, that's the magical speed you get. And you see if you look at the bottom right, which is the marketing number, right? The max speed for the largest possible channel and the largest number of streams and 256 QAM, you get close to 7 gigabit per second. That's the max speed you can get or expect to get one day with 11AC on an access point that's 160 MHz channels and supports 8 streams, and supposing that you can do 256 QAM to that access point. In practice, of course, it will take years before we get to 8 streams, as you know. 256 QAM is very close to the AP, and 160 MHz, well, we don't have those yet in many places. So you probably will use something more inside the table for a while. But, that's the marketing number, the max speed. And in the dream rate, you say, well, because the access point does all that, and you can use MU-MIMO, maybe you can combine stations with different capabilities and use all that possibility in a cell on the way downstream. For example, you have one AP, 8 stream, 160 MHz, MU-MIMO support, and to that you associate one 4-stream client. That is also, say, 160 MHz client, maybe a big laptop or something. This one may be getting all the way up to 3.47 gigabit per second, MCS. And on the same access point, at the same time, you may be associating another client that would be a 2 special train client, and the AP is going to send to that client at the same time, because of MU-MIMO, some traffic, and this guy will get at the same time as the other one gets 3.47, this new client will get 1.73. And maybe you can add 2 other clients, and it will be 1 special stream each, and they will each get 867 megabit per second. And because of MU-MIMO, we do all that on the way down. Okay, so that's the throughput of the cell in theory. Once everything works, when we have the speed that we hope for, etc. Again, it's going to take a while because there is no 160 MHz client, and there is no certification that mandates that kind of size for the client. And also, you cannot combine the streams that easily yet. So that may happen one day, but it's not there yet. Okay, what about protection? Well, for the frame protection, we use the same logic as 11N, and that one works well, where you send that slower part of the frame first to tell that you're going to send for a certain duration. So that works well. We use it for 11AC as well. So for the channel protection, we learned the issue with 11N. So 11AC also protects against these channel size issues, 20 versus 40, that we didn't think of for 11N. And the way it works is that if you want to send some traffic and you realize that your client is not sending you the same size of frame, 40 megahertz, for example, than you would expect, then you are going to send a request to send on all channels that you plan on using, for example, 4 times 20. And then your client is going to maybe receive some of those and maybe consider that some of those channels are not usable. So it's going to return a clear to send only on those channels that are free at the client level, not source of any interference. So the result is that the AP is going to learn from this exchange why the client is not responding on all 4 channels. And of course, the AP is going to consider that these 2 channels at the bottom are not usable because there is a problem on the client side that the AP doesn't see. And it's going to use only those channels that are working well. That's pretty clever. There may be some other issues we're not thinking of yet, but that is going to be a good protection. This is going to happen every time there is an issue in the communication. That is to say, there is asymmetry in the communication. You communicate at 40 megahertz and the client responds at 20, or you communicate at 80, the client responds at 20 or 40. Every time that happens, we'll use that test to indicate what kind of bandwidth can be used on each side. All right, so what about these waves? You probably heard of those, wave 1, wave 2. Thing is, of course, the industry is very eager to get 802.11ac data rate. So as the work was still being done in 802.11ac, the draft was taken by the Wi-Fi Alliance, and the first certification was designed to certify devices that will implement that first draft, which is actually draft 3 of the 802.11ac protocol. And it's only implementing part of what can be done, but something that can be done at that time. So that's what we call wave 1. It certifies access points that can do 80 megahertz. It certifies 3 special streams. It doesn't certify MU-MIMO. At that time was still too early to decide exactly how MU-MIMO would be working. And also 256 QAM is described, but it's optional. But most vendors that implemented Wave 1 devices did implement 256 QAM because it looks nice on the paper, regardless of what distance you can really get. Then in 2016, there is a Wave 2 phase of 802.11ac, where this time the Wi-Fi Alliance takes the final amendment, 802.11ac, that was published last year, and is going to certify devices that can do all the way up to 160 megahertz for the access points if they decide to do so. Clients can still do 80. And 4 streams. And this time, MU-MIMO can be tested, and 256 QAM can be tested as well. So that's wave 2. And of course, as the technology improves and we may be able to do more than 4 streams, maybe 5 or maybe 6 or maybe 7 or 8, there will probably be new waves or new certifications that may be improving on wave 2. But in between, of course, there are some other amendments that will be coming out that may be also improving the way we send frames or we manage the time or the space. And you may have some hybrid Wi-Fi certifications that may be validating more streams, but also some other features issued from some other parts of the 802.11 standard. But that's the future.